Explanations of superposition usually talk about being in two places at once or being dead and alive at the same time. That's not only confusing but also incorrect. But turns out we can actually understand superposition more clearly without analogies. There is a famous experiment that naturally shows why superposition makes sense and why it's so central to quantum mechanics. Hi, I'm a physicist and this is how the Stern-Gerlach experiment explains superposition. Superposition is the feature of quantum mechanics. It's responsible for a lot of the weird stuff, and quantum mechanics is confusing in part because this fundamental feature is so difficult. Trying to make sense of it, we often torture a cute cat and say it's dead and alive at the same time. A hypothetical cat, of course. But this dead and alive thing, that's not quite correct, as you probably guessed. This language is oversimplified. The cat is not dead and alive, it's in a superposition of being dead and being alive. But that doesn't explain anything. Maybe a cat is not the best way to think about superposition. So let's say goodbye to the cat for now and switch from analogies to an actual experiment. But don't worry, I'll show you a few cats along the way to make the goodbye easier. So let's use the Stern-Gerlach experiment to understand what superposition is all about and why quantum mechanics needs superposition. So, what is the Stern-Gerlach experiment? This experiment measures the spin of particles. Here we don't need to know what spin actually is. Let's say it's a property of a particle, like an electron. You probably know that it can be spin up or spin down. That's true if we only look at one spatial direction. The particle can have spin up or down in x direction, but it can also have spin up or down in y direction and z direction. So, it's spin up and down for each direction. For each direction, this property has two possible settings, two different values. Now, the experiment measures the spin in one direction, for example along the y direction. How? With a magnetic field, which changes along that particular direction. Let's say we shoot particles which should not interact with the magnetic field, at least according to classical physics. But as they pass through this field, they are deflected. The field splits the beam. Why? Because spin behaves like angular momentum and generates a magnetic moment, and the magnetic moment interacts with the magnetic field. So, the beam is split up into spin up in y direction and spin down in y direction. To be precise, the experiment uses silver atoms, and the spin that's interacting with the field is the spin of the atom's valence electron. But that's a technical thing. For our purposes, it's enough to just think about electrons. That's why I'm going to use the word particle from now on. Importantly, the particles are distributed according to their spin in y direction. Half of them are landing here and half of them here. So, we have a measurement device for the value of the spin along a certain direction. Now, things become really interesting if we combine multiple measurement devices. If we measure the spin in y direction and then again measure the spin in y direction, we get the expected result. All particles that had spin up still have spin up. But what happens if we measure the spin in y direction and then the spin in x direction? You probably guessed it, half of the particles that had spin up in y direction also have spin up in x direction, while the other half has spin down in x direction. Okay, but what happens if we now measure the spin in y direction again? So we make a first measurement in y direction and only proceed with those having spin up. We make a measurement in x direction and then another one in y direction. What happens? We started with particles that have spin up in y direction. Do the particles still have this property after the measurement in x direction? No. We get 50% spin up and 50% spin down. That is odd. Let's look at some cats while we think about it, and meanwhile you can now hype my videos. This really supports a small channel like mine, so thanks for your hype points and your likes. So, we started with particles that had spin up in y direction, but now it seems like whatever came before our measurement in x direction doesn't matter anymore. It's like the measurement in x direction kinda destroyed the one in y direction. Like, we can only measure a definite spin in one direction and all others direction can't be definite at the same time. We conclude we can't measure the spin in different directions simultaneously. This is one of the major problems interpretations of quantum mechanics have. Can't we measure it simultaneously simply because our abilities are limited? Or is there an underlying truth? Do particles only ever have definite spins in one direction. I'll come back to this, but I really want to know what you think. So, the measurement in x direction has two effects. First, we get a definite value for the spin in x direction. Second, we destroy the result of the previous measurement in y direction. While this is already quite peculiar, it's gonna get weirder and more fun. We again start with particles that have spin up in y direction and then measure the spin in x direction. The beam gets split up, but now we're using mirrors to bring it back together. So we are mixing the particles with spin up and down in x direction. What happens if we measure the spin in x direction again? We get 50% spin up and 50 spin down. That's rather intuitive. I mean, we just mixed 50% spin up and down. The thing is, it seems like we actually destroyed the measurement in x direction. You will understand what I mean if we replace the last measurement with a second measurement in y direction. What do you think? What do we get? Do we get 50-50? I mean, that's what we got prior to mixing the beam. Well, now we get 100% spin up in y direction, the property we started with. It's like the measurement in x direction didn't happen. That's what I meant when I said the mixing actually destroyed the measurement in x direction. Remember, the measurement in x direction had two effects: a definite value in x direction and the destruction of the result of the previous measurement. If we undo one of the effects, we automatically undo the other effect as well. If we undo the measurement in x direction, we reconstruct the definite spin in y direction. And that leads to a surprising conclusion. What seemed like two separate effects may actually be the very same thing. A definite spin in one direction is the same thing as indefinite spins in the other directions, at least from our perspective. By reconstructing the indefinite spin in x direction, we also reconstructed the definite spin in y direction. If one direction is definite, all others are indefinite to us. And you can swap this around. Definite spin in y direction means indefinite spin in x direction and vice versa. This indefiniteness, that's what we call a superposition. If a particle has spin up in y direction, it's in a superposition of spin up and down in x direction. This does not mean that the particle has spin up in y direction as well as spin up and spin down in x direction. From our perspective, particles can only have a definite spin along one direction. It means the particle has spin up in y direction, but no definite value in x direction. In that sense, superposition is just a description of something we don't know. But we have some requirements for this something we don't know, because we want to be able to mathematically describe all this. We need to be able to mathematically describe this indefinite spin that has two different measurement outcomes and is linked to a definite spin in another direction. Superposition is a mathematical description of this. If we have a vector describing spin up in y direction, this vector can be expressed in terms of a linear combination of two vectors describing spin up and down in x direction. So, superposition acts like a linear combination of vectors, and that's where the name superposition comes from. Importantly, superposition is the mathematical description of some kind of indefiniteness. It doesn't describe a cat that's dead and alive, but a cat that could potentially become dead or alive. Is this indefiniteness reflecting our inability to measure precisely, or is it reflecting an underlying truth? That's exactly what interpretations of quantum mechanics are trying to answer. Copenhagen says it reflects a fundamental truth: the particles possess multiple spin states simultaneously until the act of measurement. Many World also says it reflects a fundamental truth, but because all spin states in the superposition are real. But Pilot Wave, for example, says that particles have definite positions and trajectories. So superpositions reflect our inability to measure precisely. As far as I understood it, it also says spin isn't there until you measure. Spin is more of an illusion. If you want to know about this, please let me know. If you want to get a better intuition for superposition, take a look at another experiment, the double slit. Thanks for watching. Have a wonderful day.